let's now talk about tangent planes. So the setup here says, let's say we're studying a surface that is smooth at a particular point. Remember, when we say this term smooth, what we mean is that the standard normal vector, which is obtained by taking the cross product of our two tangent vectors, is not equal to the zero vector. Under this condition that we're studying a point that's smooth, meaning this normal vector is not the zero vector, it turns out that this vector is normal to the tangent plane to this surface at this point. What this means is that we can use this normal vector to write down our formula for the tangent plane at any point. So the generic figure looks like this. Here we have our generic surface, and let's say we choose a point where the standard normal vector is not the zero vector. The idea is that this is the data of one point and one normal vector, which is exactly the data we need to write down the point normal equation of our tangent plane. So let's go back to our example that we just studied of the double cone. For the double cone example, the parametrization was bold x of r theta equals r times cosine theta, r times sine theta, and little r. And we previously calculated the standard normal vector, and the vector we got was negative r cosine theta, negative r sine theta, and then r. Well, let's say that we set little r equal to 2 and theta equal to pi over 6. So this will give us a particular point on the double cone. The particular point is obtained by plugging in r equals 2 and theta equals pi over 6 into the parametrization of the surface. What do we get when we do this? Well, we get 2 times cosine of pi over 6, which is the square root of 3. Then we get 2 times sine of pi over 6, which is equal to 1. And then we get 2 as the third coordinate. So we're studying the point root 3, 1, 2 on this double cone. And then what about the standard normal vector? Well, for the standard normal vector, we again plug in 2 and pi over 6 into the formula for the standard normal vector. Here we end up with negative 2 times cosine of pi over 6, which equals negative root 3. Then we get negative 2 times sine of pi over 6, which is negative 1. And then we get r equals 2, so 2 as the third coordinate. So this is the data of a point vector and a normal vector, which is exactly the data we need to write down the formula for the plane tangent to the cone at our point. This is a typo that I'll fix in the slides. The point we're studying here is not 0, 1, 1, it's root 3, 1, 2. So I'll make sure I fix that in the slides. So what is the plane tangent to the cone at the point root 3, 1, 2? It's the plane with point vector root 3, 1, 2, and normal vector negative root 3, negative 1, 2. That's exactly negative root 3 multiplied by x minus root 3. Then we subtract 1 multiplied by y minus 1. And then we add 2 multiplied by the quantity z minus 2. And that whole expression has to equal 0 in accordance with the formula of the point normal equation of a plane. So by plugging in a specific r value and a specific theta value, we get one point on our cone, which is root 3, 1, 2. So again, this point we're studying is root 3, 1, 2, not 0, 1, 1. And the particular normal vector we're studying is negative root 3, negative 1, 2. This is exactly the data we need to write down a point normal equation for our plane. Finally, I want to address the issue of surface area. The idea here says that we can approximate area inside of a surface at each point. The idea is that if we choose a point, we can look at our two tangent vectors t sub little s and t sub little t, where little s and little t represent the two variables that go into our parametrization. And these two tangent vectors can be used to create a parallelogram that approximates area at this point. Remember, this is a figure in 3 dimensions. And in 3 dimensions, to calculate the area of a parallelogram, what we really want to do is we want to look at the magnitude of the cross product of these two vectors that span the parallelogram. So the idea is that area density in this surface is measured by the magnitude of the cross product of our two tangent vectors. And we now remember that the cross product of these two tangent vectors is exactly how we define the standard normal vector. So area density is the magnitude of the cross product of our two tangent vectors, which is also the same thing as the magnitude of our standard normal vector. So this inspires our definition of surface area for a parametrized surface. Let's say the surface S that we're studying is parametrized by bold X, which is defined as on some domain D in R2 into R3. Then the area of our surface is equal to the double integral throughout the domain of the parametrization. And here we are integrating the magnitude of the standard normal vector with respect to area here. So let's finish this lecture by looking at our cone example once again. So here we're writing down again the formula for the our parametrization of our cone, where we're invoking cylindrical coordinates here. So here, bold x of r theta is r times cosine theta, r times sine theta, and then little r. And here we're choosing r to range from 0 to 1, and theta to range from 0 to 2 pi. Remember, we previously calculated the standard normal vector, and we found that the coordinates were negative r cosine theta, negative r sine theta, and then little r. Now, since little r is ranging between 0 and 1 here, what this means is that we're just looking at the top part of our cone, and we're terminating it where z is equal to 1. And remember that when we calculate surface area, what we end up needing to do is taking the length of the standard normal vector. And here the length is obtained by squaring the coordinates, adding them up, and then putting the result under a radical. Here we're looking at the square root of r squared cosine squared theta plus r squared sine squared theta plus r squared. When we sum everything up under the radical here, we get 2r squared, and when we take our square root, we get little r times root 2. So now we're looking at the top part of our cone, where the cone terminates when the radius is 1, or which is the same as z equals 1 here. And what is our area? Well, according to the definition, we should take a double integral over the domain of the parametrization of our surface. So here what that means is that we will integrate dr d theta, where r ranges from 0 to 1, and theta ranges from 0 to 2 pi. Again, when we calculate surface area, the function we're integrating is the area density function, which is the magnitude of the standard normal vector. Well, we just found that the standard normal vector was r times root 2. We can factor out the root 2 from the double integral, and now we're taking a double integral of r dr d theta, where again, r is ranging from 0 to 1, and theta ranges from 0 to 2 pi. Now we can do the double integral. So if we integrate r from 0 to 1 dr, we end up with just 1/2, and the 1/2 factors out. So now we get root 2 over 2, and we're integrating theta from 0, another typo, this should say 2 pi. When we integrate theta from 0 to 2 pi, we just end up with 2 pi. So the result is just the square root of 2 here. So this is telling us that the surface area of our cone is the square root of 2. One last thing to mention here is that this cone, according to our parameterization, has the top open. If we were to close the top here, we would have to add something to our surface area calculation to account for the disk that would cap off the cone. In our case here, that would be the circle of radius 1, so we would need to add pi to this calculation. But according, our parameterization is not accounting for any cap on our cone here, so the area is simply equal to root 2.